Today I will talk about some projects I started since my postdoc, because my PhD was about early Earth processes, and since the postdoc, I started to work on this small icy body called Enceladus, which is a small moon of the Saturn. And like Nick said, I'm mainly interested in the chemical composition, including the nutrients and organics. And I will also, at the end of this talk, I will also cover the habitability issue, which could be applied to other acid moons in general. Because I know some of you are probably from the astronomy field, so probably it's more relevant with you about this habitability issue. So when I started this with a famous painting by this Paul Gauguin's picture. So this is the title of this photo is "Where do we come from? What are we? And where are we going?" It corresponds to three major questions that asked by our called the astrobiology, the field, the new interdisciplinary field. So what do we come from correspond to origin of life, and what are we corresponds to the definition of life, and are we alone? And actually, the definition of the life is not like people have different definitions yet currently. So we don't have a very widely agreed definition of life yet. So that's why we need to find another example so that we can better define life. And where are we going is other habitable planets like colony on Mars and Mars space station and other even exoplanets in the future. So I'm particularly interested in the planetary oceans because we know that the planetary oceans is the habitats for all of life as we know it, especially for the microbials that originate on the Earth, and the life has a very long history that only lives in the ocean, probably even to this mid Proterozoic, in the middle stage of the Earth, that life started to land on the Earth, on the land, and also I'm interested in we have any other ocean bodies that could have the origin of life or could be habitable for life. And currently we know that there are several ocean bodies in the outer solar system, the Sirius as asteroids in the asteroid belt, and then with several acid moons with known of the subsurface oceans, and also Pluto. And today's talk I only focus on the Enceladus, but my group is also working on other acid bodies, and we show that they have some similarity in terms of the habitability as well as the composition. And my group is particularly interested in the water chemistry because we know that this is the major elements in the universe. It's mainly made of the hydrogen and the helium and some oxygen. And the universe evolved into this rocky planets like crust composition, which is mainly made of silicon oxides and aluminum calcite, calcium, those things. But then if we compare the cellular composition with the crust, with the universe, we find that it's very, very different. But if we plot the cellular ratio, this is cellular ratio normal to the carbon, amount of the carbon, and you can see this is the water chemistry, seawater chemistry, and this is the cellular ratio. It has a very nice log linear correlationship between these two compositions. It basically shows that the water is actually, the water chemistry matters because the water can dissolve the rock to free those nutrients, to free the elements that for the buildup of the cellular life. So today I mainly covered some major elements like carbon, nitrogen, and some also bioessential nutrients like phosphorus, and also more importantly is this part. It has a very low abundance, so very hard to detect using some current emissions. But those elements are very critical to build up these enzymes. Like for example, the nitrogen fixation it used the molybdenum in this called a cofactor. It's an active center that can dissociate the nitrogen to nitrogen, the triple bond, and very efficiently, so that it can fix the nitrogen for the whole ecosystem. So I will briefly also cover this topic, but like I said, it's really like unknown, and Nick and I are discussing about some collaborations to answer these questions. And I will briefly cover the exploration history firstly, about the, that you get familiar with this small acid body if you haven't been. And the Enceladus was discovered firstly by William Herschel in 1789 by a telescope built by him. And back then it was just a single dot, like merely observed by this telescope. And it is the 6th largest moon of Saturn, with the 500 kilometers in radius. So it's around the size of a medium, like a state in US, or a province in China, or a country in Europe. So sorry. But it's thought to be, it's covered by the thick layer of the ice, because the surface is just a space temperature is very low. It's like minus 200 Celsius degrees C, and it is located in the E ring of the Saturn, and some latest studies showing that the E ring actually comes with the material comes from this Enceladus. It's made of the icy grains, like erupted from the Enceladus. We, before the Voyager, we saw that the icy moon, all the icy moons, like including the Enceladus, is just like our lunar moon. It's a dead moon without any like a magmatic activity, no enough heating for liquid water to occur. So it's just a rock with some ice covered on it. But Voyager took some close pictures of this icy moon, and from this picture you can already know that it has a very different, for example, distribution of the impact craters than the lunar moon. And if you know that the density of the craters, actually you can use an equation to calculate the age of the surface. So it means that at least some surface, for example, especially in the southern hemisphere of the Enceladus, it is much younger than the lunar moon, than the lunar surface, as well as the southern part. And it basically showed a very overall very young surface, and the big difference in the crater density shows the big age difference. And people start to think, why the crater density is so different. Also, the age is so different. Also, it shows some topographic relief, with the terrains could be 1 and 2 kilometers high. Also, some cracks, for example, like these bands. And then people start to use some geophysical models to try to understand why you can have this very smooth surface, and develop some models showing that with tidal dissipation you can have some enough energy to support at least some partial melting of the ice with some subsurface water pockets. And then NASA launched the Cassini-Huygens mission. So the Cassini is mainly for this various icy moons, and the Huygens land on the Titan. And the Cassini showed a very, very astonishing features of Enceladus. For example, it shows these tiger straps, which you can show is a much closer picture of this part, southern hemisphere, and with valleys with this kind of terrains that could be kilometers high. And if you are familiar about the Mars, it looks like some liquid water flowing and got frozen to form this kind of structure, cracks. And the most exciting discovery, I think it also the only plume observed in the solar system is the water plume from the source pole of the Enceladus. So actually, NASA allocated more time to try to orbit and try to collect some samples from the source pole and analyze the composition of this plume. And the talk will mainly focus on the results by this plume. And Cassini also did some geophysical measurements. For example, the thermal anomaly as well as the mass anomaly. And basically, it showed, at least in the source pole, it showed a very high thermal anomaly aligning very well with this cracking structure. For example, like here, like tiger straps here. And also the large mass anomaly at source pole. And people use the models to try to understand why there's a mass anomaly here and suggest a very large, at least the regional subsurface ocean, like 30 to 40 kilometers in depth below the acid shell. And right now we know that the Enceladus ocean, with more data collected, and we know that there's a global subsurface ocean, liquid water ocean, beneath this icy shell. And my second part of the talk, which is a major part, is about the ocean water chemistry. So since Enceladus collect some sample and analyze the composition and what we know from this. And this is the two very useful payload on the Cassini. One is called the cosmic dust analyzer. So it analyzes some ice grains from the E-ring, and it showed some results I will show later. And also, the Cassini flies through the plume in the source pole of Enceladus and analyzed using a payload called the ion and neutral mass spec. And it gave that it shows very, very promising or exciting results, showing a mixture of the gases like composition. Like it has water for sure, and some hydrogen, some methane, some ammonium, some carbon monoxide, and possibly hydrogen sulfide. So if you are familiar with some like water around you, this kind of water with these smelly gases, usually you find it in some bog waters with very low oxygen. But this water chemistry is actually what we want to have for the early Earth when the life started, because the reducing environment is good for the synthesis of organics, also the stability of the organics. And the Enceladus plume also, there's a variety of organic compounds ranging from C1 to C7. Actually, there are some results showing that probably it could be even beyond the C7. But due to this capacity of this payload on the Cassini, that we can't tell exactly what's beyond the C7. And the cosmic dust analyzer also analyzed the salt composition of this plume and acid grains. It found that it is rich in sodium chloride and also sodium bicarbonate and sodium carbonate and potassium chloride. So if you have this in the kitchen, this is soda, right? And if you want to neutralize some acid, you use this one. And if you dissolve these salts in the lab, it will show that it is an alkaline pH. It's probably pH around 8 to 10. And more interestingly is that with these salts, we know that it shows a sign of active dissolution of the rock by the liquid water. As I said, this is critical for the habitability of life, because the life requires the dissolution of the rock by the water to release those nutrients for the life. And people also suggest that it's possible hydrothermal fluids, because in the plume they found that the sign of the nano silica particles. So we sometimes use the silica as the jewelry, and if you just throw it in the water, it won't dissolve, right? But if you cook it with the hot water, the solubility of the jewelry, the silica, greatly increase with temperature. So that's why when people analyze this, observe this silica in the icy grain, people think, oh, there must be some hydrothermal activity that dissolve this silica with a substantial concentration that, when this got the quench freezing, it can preserve as a silica nanoparticles. So that's the evidence that for the hydrothermal fluid. So when we collect these acid grains using this analyzer, we actually need some lab calibration to use this acid grain chemistry to reconstruct the water chemistry. Because when the acid grain impact the, for example, dust analyzer or mass spec, it will generate some secondary reactions because the speed is very fast. It's like kilometers per second. Very, very fast situation. So this is the lab in Free University of Berlin by my colleague Frank Postberg. So his lab is actually probably one of the few or previously is the only lab that can do this calibration to simulate the impact of hypervelocity acid grains from the ocean world in the space. And with that, we can know the water chemistry is with a possible pH of around 9.5 to 11, and with a very high concentration of hydrogen. So these different squares are the water chemistry observed on the Earth, and this is the Enceladus. So Enceladus is very close in the water chemistry to the lost city, also the Saturn. The Saturn is the continental synchronization reaction site. So this is the lost city. So when people found the lost city, they also found the abundant life, even some crabs or shrimp in the hydrothermal vent. So with this water chemistry, you can support a ecosystem, even some animals. So people start to suspect that this should be very habitable. And this is currently what showed by the Cassini mission about the detection of elements, including carbon, nitrogen, oxygen, silica, chlorine, hydrogen, and sodium, potassium. But we don't know the availability of other bioessential but very minor elements. For example, the phosphorus, sulfur, and all of these transition metals, as I mentioned earlier, to form these enzymes. But if we look into this elemental cycle in the Enceladus, it was very different from the Earth. In the Earth, you have the mountains, which have the rainwater, will dissolve this rock, and by the rivers, it will deliver this to the ocean, right? But for the Enceladus, you just have a whole rocky core, and in a global ocean. It's like you threw a sugar or salt into a glass and let it dissolve for billions of years. So it is very simple, so we can do a thought experiment, is to assume the complete dissolution of the core, which is not true. You can see that all of these elements can reach very high concentration. And it shows that so the actual availability should be controlled by the long-term water-rock interaction. And you will form some secondary minerals whose solubility controls this availability of nutrients. So that's what I did. So I developed the model to simulate, if the whole rocky core got altered and reached some kind of a thermodynamic equilibrium with some secondary minerals, what's the water chemistry with this? And this is the phosphorus. I consider several case studies, and this is the predicted phosphorus level, and this is the modern Earth. So it basically shows that the phosphorus level in the Enceladus ocean should be higher than the ocean water on the Earth. And after I published my study, there's a Nature paper coming out by my colleague, and they showed this detection of this phosphorus in the plume. And basically, it matched the prediction results very well. So we now know that if there's any life in the Enceladus ocean, it should be short of phosphorus. So phosphorus is not a big deal there. And then my group did some further study by my student, and we reconstruct or estimate the availability of another 2 bioessential nutrients. One is iron and one is sulfur. As you can see, the iron should be much higher than the molten Earth seawater, which is reasonable because the iron in the anoxic water has a much higher solubility. But the sulfur is much lower than the molten Earth seawater because in this anoxic seawater, sulfur just don't dissolve very well. And right now, we only have some tentative signals for the hydrogen sulfide. And I discussed with some people who are working on the Cassini data, and they said basically this very low signal-to-noise ratio at this mass channel will preclude the firm identification of hydrogen sulfide. So we still need to launch some further missions with a better, detection limit to confirm this prediction. And another very important group of elements is the transition metals. Like I said, the availability of these transition metals will greatly affect the formation of these enzymes in the microbes. This is actually the theory behind this very important hypothesis, showing that if you in the early Earth, the water chemistry, the evolution of the water chemistry, especially the availability of nutrients, will determine when you will have this different kind of metabolism. But we have very limited knowledge about this. So I was thinking probably the solubility is controlled by the overall anoxic, alkaline, and carbonate-rich water, particularly the precipitation of this phyllosilicate mineral, carbonization mineral, or the carbonates. So that's why I discussed with Nick that because his group can synthesize these minerals very well, so probably we can collaborate on this to understand the availability of these transition metals. And but we can also get some evidence from the molten sublimation fluid, because for some general geochemical properties, it matches very well with some sublimation fluids on the Earth. But you can see it has very few data available and very, very low levels. Even with the modern, very good mass spec, you can still not get this data. And my group is recently also working on some the stability of some critical but puzzling building blocks of life, because this is the organics observed on the Enceladus. It covers with a lot of function groups and different molecular weight. And we are considering about the source of this oxygen and nitrogen-bearing species, because these species are the precursors to form these amino acid or nucleotides, those biomolecules. And we particularly want to understand the stability in this ocean and hydrothermal system, and which could be used for to guide us to the selection of a potential biosignature in the future. So we calculated this thermodynamic chemical affinity of this reaction, the synthesis reaction. So it's complicated definition, but if the value is negative, it means that it's less favorable to form, which means it's not stable. But if it's positive, it means that it's favorable to form. So this is the results by my colleague, and you can see the affinity for the methane is very positive in this area, and which shows that if you have this such high positive affinity, you can support at least the methanogens, a typical microbes observed in some bog waters, anoxic waters. And we did this for all of the proposed organics in the Enceladus. So the red color shows the positive values, and the blue color shows the negative values. As you can see, in the Enceladus ocean water chemistry, you basically all of the organics are favorable to form. but some very important organics like ethylene and hydrogen cyanide are not favorable to form, or in other words, not stable. But these biomolecules are critical as the building blocks of life, because they are, for example, the hydrogen cyanide that was thought to be the critical precursor to form the nuclear base for the life. And we also did so if we have these thermodynamic properties, for example, for the formate, is it will it occur in nature? Actually, there are a lot of studies on this observation in the modern hydrothermal fluid or modern like anoxic waters, and they found that given some long time, you can have this kind of equilibrium ridge. For example, this is the formation of the formate observed in the modern, like this is a hydrothermal vent mixed fluid, and it means that given this thermodynamic like a thermodynamic driving force, those organisms could be formed in the Enceladus ocean for the potential origin of life. But we found that, so if you have this so in these organics like a formate or carboxylic acid, these are favorable to form. But for some critical like precursors for the origin of life, like hydrogen cyanide, is not stable at all in this fluid. And the real awkward thing is that the half-lifetime of this compound is very, very short. Like if you can see, this is the log K1 in the seconds. So it will degrade very soon, especially if you have some hydrothermal fluid. It means that if you can observe this compound in the plume and for a long time, it could be a strong sign that there is life in the ocean, because the life can generate this stuff out of equilibrium. So I will talk about, I showed the availability of nutrients and the availability of the organics, and I will show you mainly the habitability implications in this section. And I think the most important aspect of discovery, the azimuth discovery, is that it greatly expands the traditionally thought the habitable zone definition, because the habitable zone definition was defined by the ability to support the liquid water on the surface of the planetary body. But if you have these azimuths that have the subsurface ocean with the very cold surface, then the habitable zone, the definition could be largely expanded to even to the outer solar system. And this is also very important for the exoplanet study, because we know there are like more than 5,000 like confirmed exoplanets of different kinds of exoplanets. And but we think that at least from the solar system perspective, like if you have 8 like a large planetary bodies, but you have massive amounts of these azimuths and asteroids, which have the subsurface ocean. So in theory, there must be much more than these 5,000 azimuths in those around these exoplanets. It's just that it's too small for our detection, so we just can't find it. And if we can find this, at least for some water chemistry, then we can know this probably those bodies are also potentially habitable. So the next question is how to confirm the subsurface oceans and analyze their composition in the exoplanet system. It's very, very challenging. And I talked about this issue with my astronomy friend, and he told me that it is not far, that probably the work is probably already submitted, is that we will have the first detection of the azimuth very soon. And so if we can have this ocean, either in the solar system or in the exoplanet system. Another very important aspect is the availability of nutrients for the life. Because if you can see, this is the Earth, and this is the Enceladus. This is the relative availability of the nutrients. So it's totally different picture. So we can't use the Earth, the current Earth understanding to kind of extrapolate the habitability of those acid moons, because they have very different availability of the nutrients. And another one I think is more threatening is the availability of the building blocks of life. Because here, this is the thermodynamic work. It shows that, although some simple organics could be thermodynamically favorable to form or stabilize, but for these critical biomolecules like glycine, amino acid, they are not stable. And there are already some kinetic studies showing that it has very fast degradation kinetics of this amino acid in those acid moons. So how can you accumulate high concentrations of this biomolecule for the origin of life? And another aspect is about the availability of the energy, because in the modern Earth, more than 95% of the energy support the surface ecosystem, support our food, comes from the solar energy. But for those acid moons, it has like kilometers thick of the acid layer isolated from the sun. How can you generate enough energy? So people thinking that maybe the tidal dissipation or some chemical energy could be available for this small ocean world for potential life. But I think even if you have this limited source of energy, it can support only a weak ecosystem, very, very low productivity. And, right now on the Earth, we have the sun like radiating the surface. We have the mountain like keep this Wilson cycle. But for the ocean, for the acid moons, how can we update the substance in this like billions of years old ocean? And there are several ways. One is by the impact. If you have the impact, like just cracking this icy shell, you can deliver some new substance to the subsurface ocean. Another way is that the people propose this like a cryovolcanism or subduction of these ice layers. Actually, people found some relevant observations on the Antarctic or Arctic. You can have this like ice gliding and transport some material from the surface to the subsurface. And I think probably this question relies on you very much, is the evolution of all of these features. Because the acid moon system relies heavily on the tidal dissipation, but we don't know the evolution of the orbits of the acid moon. How did this acid moon form? And what's the original position, and how did it evolve through time? So this is the current understanding of the tidal dissipation rate for the Enceladus. As you can see, it could be anywhere. So if someone can find a better understanding about this evolution, so it can really solve the big problem for the evolution or for the evolving habitability of the acid moon. Because we know that life requires for a very long time to originate. So if this acid moon system is not very stable through the geological history, then it has a very limited chance for the origin of life. And perhaps more importantly is the in situ origin of life. So for the Earth, we know that the conditions for the production of building blocks of life and the conditions within which unknown life could be active are totally different from the conditions that for the origin of life. It requires much stricter conditions to originate. But like for example, with the Earth, you need to have a wet-dry cycle for this like single biomolecules to form polymers, to form the enzyme. But for the acid moon, how can you have this wet-dry cycle? Because it's full of water. This is just one simple example. And I think we should emphasize that what Enceladus doesn't have probably matters more for the in situ origin of life. And if there were life in the subsurface of icy moon, how can we detect it is another big challenge. Because for the exoplanet, you can detect the information from the spectra of the atmosphere. But for the icy moon, it is, most of the icy moons don't have the atmosphere. And how can you detect this below the thick layers of the ice? The biosignatures is another challenging task. So this is the take-home message. So I show that it has abundant nutrients such as the phosphorus, but very low concentration of sulfur and the transition metals for potential life in the Enceladus seawater. Is very different from the modern Earth seawater. And I also show the stability of various organics, but instability of some key biomolecules for origin of life in the Enceladus seawater. And altogether, I want to emphasize the dynamic habitability, which depends on limiting factors such as transition trace nutrients, biomolecules, active supply of energy, and the complex system settings. So with that, I will thank my collaborators and thank you all for coming. And this is my lovely group in China. So you're all welcome to visit my group in the near future. Thank you. Great. A lot of chemistry. Yeah.